Uh, Hello, Mr. Morgan. I hope this video won't be too much of a hassle for you. I just want to say that I hope that you're spending good time with your family and spending your holidays well, not spending your time like in front of the computer like I have been. Yeah, see? Anyway, that's music. Um, the thing that I want to do today is I'm going to try to explain one important concept to you in ideas to implementate. Oh, I can't even pronounce the word. Ideas to implementation, and I just want to see what you think, and whether I've explained it well enough, or whether if you see that a syllabus dot point that I'm missing, then please say it out. So before I begin explaining, I would like to start off with some history. So we'll start off with the 1960s. Okay, so let me just fix that up. Okay, well, okay. Where we have Newton on the one hand, and he was British. And basically, at this time, what Newton did, he wrote a book called Optics. So basically, this was the Book of Light. Book of Light. So all the British scientists were really happy, and they all basically in this book he explains that light is particle. So the British are in favor, while the Euros or Europeans not in favor. Sorry. We also have this other guy. I'll explain why the Europeans aren't in favor. We have this other guy called Hirogen. I think that's how you pronounce it. He was European. He also wrote a book, but just except in this book, he said, light is wave. Oh, and from this book, I forgot to explain, Newton could explain reflection, refraction, and he imagined it as a projectile. Huygens could equally explain these. The British scientists were not in favor, while the Euros were. So then there was this great debate. So yeah, that was in the 1960s. Now we reach 1910 with Young. Right down here. Oh, by the way, I'm holding the camera with my left hand, so yeah, it's a little bit difficult to write. And basically, what he does is his double slit experiment. So what it is, it uses diffraction. Basically, he has a wave coming in. Imagine that these lines are the crest of each wave. When they hit this wall, they're going to reflect, but through these small holes, they're going to refract, and they're going to become sources of light. And go out like so. So at the points where these cross, there'll be constructive interference, and likewise there'll be destructive interference. And here he had his that's horrible, photographic film. From here he managed to observe a pattern like this. So these dark spots indicate the area of constructive interference. What was more important, that the darkest spot right here was right behind the boundary. So obviously, it was also very important that Young up here was British, because if he was European, then it would be deemed by the British to be like not a valid experiment. Yeah, so context always relates to the scientist. I think that's one of the outcomes. So the most darkest spot was right between this barrier. So how can you explain this pattern using particle theory? The answer is you can't. You had to imagine light as a wave. And this experiment was done more than once because at first the British scientists didn't believe it, but then later they admitted to the Europeans, yeah, you're right. So, yeah, light is wave. Alright, awesome. So, we're comfortable with the idea that light is a wave. Let's keep going on with the history. Let's go to Hertz. Hertz was a brilliant guy, nonetheless. Like, I don't know why they say that he failed to explain. I don't think he failed, I just think that he couldn't come up with it. He didn't fail. Anyway, so Hertz does some crazy experiments. Well, what a great way to put it. Anyway, let's fix that up. This is his first, and this is his receiver, or second. Basically, when the spark jumped here, another spark jumped here. So, wait, maybe I should have hit this point before. Maxwell predicted that there was a range of light, and the only ones that have been discovered is visible light. Hertz was discovering radio, Marie was discovering gamma and X-ray, and you have a bunch of other scientists discovering more. So Hertz was pretty convinced that there was an EMR wave going from here to here and causing this gap. So if it's an EM wave, if EM, what to test? So let's test. What are some properties of EMR? Well, they reflect. So he tested whether it reflected, and it did. They refract. That also went out. There's another one which I'm still slightly confused on. When he rotated this 90 degrees, there was no spark, so which suggests that light was polarized. That one I'm still a little bit uncertain, but I'm still going with it. So if there's one thing that Hertz can do to definitely make sure that it's EMR, what is it? Well, EMR travels at the speed of light. And does this work? Well, this one was like really the barrel. Ultimately, yes, it also does work, so therefore EMR. What he did was he created a standing wave. Had his mirror here and his receiver. He calculated, he can set frequency. He measured lambda. I'm going to cut this a little bit short, it's getting a little bit long. Basically by moving this back to create another standing wave, and then V equals F lambda. Basically this was actually half lambda, so you had to times it by 2. And yeah, he got 3 times 10 to the 8. He was very, very close to the real value of speed of the light. But there's one thing that he couldn't do, and he couldn't explain what he was actually observing here, was the photoelectric effect. Yeah, don't laugh. No, but that's my abbreviation for the photoelectric effect. So how does this work? Let's go to the next person. I think this guy who I always have trouble pronouncing is Leonard. Yeah, Leonard. I think he was Italian. I don't know. I forget. But basically, he did some observations which did not comply with classical physics. So this is where experiment, how to put this, doesn't fit or collides with theory. Okay. So Planck comes along, and he suggests that light is quantized. Actually, no, he didn't suggest that light was quantized. He suggested that the EMR or the isolations in the black body is quantized. Yeah, so I'll just put dB. So, and he said that it was a mathematical solution. Because he didn't actually believe it himself. He couldn't believe that BB was quantized because the energy in a wave. Where's the energy in a wave? It's everywhere. And then along comes Einstein. What did Einstein say when he wanted one Stein? He said Einstein. This is his new theory of light. So it becomes in packets. And he named it photon. So this actually really relates back to particle theory. Yeah, I'm going to cut this video short. I'm sorry, it's been 12 minutes. But basically what he did was he explained the photoelectric effect using particle theory. So now that he's done that to a really good degree, do you see what's the problem? We have one experiment that says wave, but then yet we can't explain another thing unless we say particle. Now I know that today that we say that light is both particle and wave, which is really cool. And yeah, that's all I got to share with you. Anyway, thanks for watching.